bit different. One is about, it just a summary and concepts of endocrine, and then the other one's hormones and metabolism. This one specifically we do not have.
All right, well, let's watch this one. And I guess my role is to ask if you've got any questions, I'll answer.
Sure. Thank you. Is
So
this for the limbic system PowerPoint that we have? Is this for the limbic
Yes,
system?
well, that's what's supposed to be happening today, is the limbic system and, what is it, endocrinology of
Emotions, learning hormones.
Yeah.
Stuff like
pituitary, limbic system, hypothalamus, pituitary, interrelationships of emotion and endocrine function. That's the one I'm looking for.
that. Okay.
This came up in that pad.
Okay.
So we'll start with this one.
Present here in this next mini lecture is not to give you a full lecture, but just to provide you with something, a quick overview. So if you go through and you look at the handouts, this is just intended to show you how you can use them and what you may need to be responsible for. So this is a quick reference summary, providing you some lists and quick indications about a little bit about the hormones. So my quick listing. So we're going to go through and we're going to look at organ by organ or tissue by tissue where these hormones are coming from. If we start with the hypothalamus, hypothalamus is the source of corticotrophin releasing factor, abbreviated as CRH or CRF, factor or hormone. It's a polypeptide. It's a source of dopamine, which is neither a polypeptide nor a steroid. It's a source of growth hormone releasing hormone, GHRH or GHRF, which is a polypeptide. Somatostatin, which is IH for growth hormone inhibiting hormone. It's a polypeptide. Gonadotropin releasing hormone, GnRH or GnRF, which is a polypeptide. Thyrotrophin releasing hormone, TRH or TRF, which is a polypeptide. Oxytocin, which is made in the hypothalamus but released in the posterior pituitary. It's a polypeptide. And vasopressin or antidiuretic hormone, ADH. That also is synthesized in the hypothalamus but released in the posterior pituitary. It's a polypeptide. So if I look at this, I can see that pretty much most everything, all of these hormones made in the in the hypothalamus, that they're polypeptides. And that immediately tells me some of their behaviors. Synthesized ahead of time, stored in vesicles, circulate freely in the blood, bind to cell surface receptors, generate second messengers, and bring about a change in specific activity of existing enzyme molecules. So fast onset, short acting. Next up is the pituitary gland, and we can divide the pituitary gland into the anterior pituitary, also called the adenohypophysis, and the posterior pituitary, also called the neurohypophysis. Now the anterior pituitary has 6 polypeptide hormones that we're going to want to remember, and well, yeah, 6. Corticotrophin, also called adrenocorticotrophic hormone, or ACTH. Follicle stimulating hormone, also called FSH. Luteinizing hormone, called LH. Prolactin, called prolactin. Thyrotrophin, which is also called thyroid stimulating hormone, or TSH. And growth hormone, also called somatotrophin, or GH, or HGH. Okay? And you put them together in the right sequence, and you can remember them by remembering flat peg. FSH, LH, ACTH, TSH, prolactin, MT, and growth hormone. So, quick way to keep those straight. Posterior pituitary, we have oxytocin and vasopressin. Remember, those were synthesized in the hypothalamus but released in the posterior pituitary. And they also are polypeptides. So if I know something's a polypeptide hormone if it's coming from the pituitary gland. Thyroid gland. Thyroid gland we can divide into two components, the follicles and the parafollicular cells. The follicles release two forms of thyroid hormone, thyroxine, also called T4, and triiodothyronine, also called T3. Now, these are neithers. They're neither polypeptides nor steroids. They're made from tyrosine, and they behave like steroids. So they're neither polypeptide nor a steroid, but they behave like a steroid because they have a slow onset, long-lasting response that they generate. The parafollicular cells, those produce calcitonin, and calcitonin's a polypeptide hormone, and that's involved in regulation of bone metabolism and calcium homeostasis. Embedded in the thyroid glands, we have the parathyroid glands, and they're a source of parathyroid hormone, also called parathormone or PTH. It's a polypeptide. Our adrenal glands, we can divide into the cortex, the adrenal cortex, and also the adrenal medulla. In the adrenal cortex, we have cortisol, also referred to as a glucocorticoid, aldosterone, referred to as a mineralocorticoid, and androgens such as androstenedione, testosterone, and hydroxyprogesterone. These are all steroids. So the adrenal cortex produces steroids. The adrenal medulla primarily produces epinephrine with some norepinephrine and even less dopamine. Now, the hormones of the adrenal medulla.
So just one little addition there. So, or a correction, testing. So the adrenal gland, the androgens made by the adrenal gland, there's not a lot of testosterone and there's not a lot of hydroxyprogesterone. It's mainly androstenedione. So just a little correction. It probably won't affect anything you're going to ever have to do for the rest of your life. But that's that.
We can just usually summarize it as epinephrine, that's the primary one. They're made from tyrosine, like thyroid hormone was, but they're neither polypeptide nor a steroid. They behave like a polypeptide. So, 4 major hormones of the adrenal glands: cortisol, aldosterone, the androgens, and epinephrine. None of them are polypeptides. One of them behaves like it, the epinephrine, but none are polypeptides. For reproduction, we have the ovaries are a source of estrogens. For instance, estradiol is the most abundant. Progesterone, relaxin, and inhibin. And the two big ones at the beginning, these are steroids. The relaxin and inhibin are polypeptides. The placenta, if pregnancy is taking place, the placenta can produce hormones, including human chorionic gonadotropin, or HCG, and placental lactogen, or PL, or also called chorionic somatomamotropin. These are polypeptides. Placenta can produce estriol, which is a form of estrogen, and that's a steroid. And it can produce progesterone, which is also a steroid. So placenta and the ovaries are sources of steroid hormones. And then relaxin, which is a polypeptide. And the testes, they produce testosterone, which is a steroid, and also inhibin, which is a polypeptide. If we're talking about the kidneys,
So, let's just go back one. So are you all aware of what these hormones do? So it's okay to know where they're coming from and whether they're steroids. But cortisol is involved in staying alive. One way of thinking about cortisol is if you have too much of it, you die. And if you don't have enough of it, you die. Okay? We don't know what it does, really. We know it's corticoid, we know it's made in response to stress. We know it goes up in a circadian rhythm type of manner. So all of you, after lunch today, you're going to get a little spike in cortisol, and every morning you get a little spike in cortisol. Right? Aldosterone is a mineralocorticoid that's involved with regulating water retention and electrolyte levels. It acts on the kidney. So this is really important for staying alive as well, and regulating your blood volume and blood pressure. Okay? Androgens. Why the hell does our adrenal gland make androgens when we've got, the gonads make in males, the testis is making bucket loads of androgens? Well, we don't know, but what we do know is that the production of these androgens increases in all of us prior to puberty. So before puberty, we have what's called an adrenarche, which is when the adrenal starts making these androgens. And those androgens act on target tissues in both males and females. And that's why we all have pubic hair. Right? It's because of these androgens. And adrenarche happens before puberty. Okay? And so there are commonalities between males and females in terms of exposure to androgens that are derived from the adrenal androgens. Axillary hair under your arms, and pubic hair mainly are the result of adrenal androgens. And then the medulla is more of a, the adrenal medulla is more of it's a staying alive organ, acute responses to stress. So the flight, fright response is from the adrenal medulla, okay? So the brain senses danger, the adrenal medulla is activated neurally, and so this is hardwired. The adrenal medulla is hardwired. There's nerves that go to it and stimulate the release of epinephrine and norepinephrine, or adrenaline and noradrenaline. And they cause an increase, or they regulate heart rate. So if you need to run away from a lion, that's the rapid response. These guys, on the other hand, the cortex, their production is controlled by hormones produced by the ACTH mainly, produced by the anterior pituitary. And so that's more of a slow response. It's more of a maintaining homeostasis and adaptive response. This is a reactive response in response to the danger. All right? So that's the adrenal gland. What's the next slide? All right, now we've got the gonads, we've got the ovaries. So, the ovaries don't switch on their production of estrogen, especially estradiol and progesterone, or any of these guys, until after puberty. So that the FSH and LH that's produced by the pituitary is going to tell the ovary to start making estrogens, and that will cause the changes in a female associated with puberty. So estrogens are the female sex steroid, and both estrogen and progesterone work mainly not just to change to induce the pubertal changes, but to prepare the uterus so that if there is a fertilised egg in the fallopian tube, it's got somewhere to implant and establish a pregnancy. So the whole idea of this is that the brain is telling the ovaries to make a steroid that not only make the steroids but ovulate an egg, okay? And if that egg becomes fertilised in the ampulla of the fallopian tubes, as it becomes a fertilised egg and a blastocyst and an embryo, when it gets to the uterus, these two hormones have caused the uterus, the inside lining of the uterus, to grow and become glandular, such that it can accept this incoming embryo to establish a pregnancy, where it will implant, all right, establish a pregnancy and make a placenta, okay? And so the placenta is another can of worms when it comes to endocrinology, because every hormone you can point a stick at is also made by the placenta. So the placenta makes lots of chorionic gonadotropin. Can anybody tell me why the placenta makes chorionic gonadotropin? You didn't cover this yet? All right, so if you get, the one thing you need to get pregnant and stay pregnant is progesterone. That's why it's called progesterone. It's a progestational hormone, okay? It is made by the corpus luteum in the ovary, which is the remnant of the ovulated follicle. This is undergraduate biology, okay? And so you have to keep this corpus luteum alive in order to keep pregnancy going. Normally, if there's no blastocyst if there's no embryo, this is a non-conception menstrual cycle, the corpus luteum actually dies and the progesterone levels go down. When the progesterone levels go down, because the corpus luteum in the ovary is dying, there's no more steroid hormone support for the inside lining of the uterus, and it undergoes the process and sheds menstruation. Okay? All right? You can't get pregnant and have menstruation at the same time. So you can't menstruate because you're literally flushing out the inside of the uterus. So you've got to stop that from happening. And the way that's stopped from happening is that the corpus luteum is kept alive by a hormone that is very similar to luteinizing hormone that's coming from the pituitary, and it's called chorionic, coming from the placenta, the chorion gonadotropin. Okay? So now the placenta is saying to the maternal physiology, it's saying, hold on, don't kill off your corpus luteum because there's a pregnancy in the uterus, we can't be empty. Okay? It keeps the corpus luteum alive, it keeps the progesterone levels high, and that then allows the pregnancy to establish. At around the 10th week of pregnancy, the placenta actually takes over the job of making progesterone. So here we've got progesterone on the list of hormones that are made by the placenta. The placenta also makes lots of estrogens. It's pumping that into the maternal circulation. That increases blood flow to the uterus. That's what estrogens do. And so so these hormones that are made by the placenta are really important for establishing and maintaining a pregnancy. One of the other ones is placental lactogen. So placental lactogen is a really important hormone because what we think that does is more so late in pregnancy, when the fetus is getting large and the placenta and the fetus together are drawing a lot of resources from the mum, the placental lactogen causes this little bit of insulin resistance. So it causes the maternal cells to be less sensitive to insulin. And what that does is after a meal, for instance, mom's glucose levels will go up, her insulin levels will go up accordingly, all right? But because she's got some insulin resistance, the glucose levels will stay high for a longer time. And during that time, the fetus can grab it. The fetus can grab that glucose. So it's a food fight that's going on between the baby and the mother. And the baby's winning most of the time because of the hormones it's pumping into the maternal circulation. Okay? Don't worry about relaxin. Relaxin really isn't important in humans, but we have it. It's called relaxin because it causes, in most animals, it causes the pubic symphysis, the ligament that holds the pubic symphysis together, to relax, and it opens up just before delivery. So all these hormones are really important to getting pregnant and staying pregnant, okay? Obviously in males we don't get pregnant, so all males need is some androgen. So the testosterone that's made in response to gonadotropins at the time of puberty not only change the male physique to cause the changes in puberty, but testosterone is also necessary for spermatogenesis. So you're not going to make sperm unless there's some testosterone around. But you also, and then inhibin is made by the testis in order to inhibit the production of FSH. And that's basically part of a feedback system that keeps the testosterone levels in check. All right? So just, any questions? Good. So we can
For reproductive big ones at the beginning, pregnancy is taking place. The placental lactogen can produce progesterone, which is a steroid, and also, and the kidneys also produce. If we're talking about the kidneys, then they produce hormones. They produce renin and erythropoietin, which are both polypeptides. And the kidneys also produce 1,25-dihydroxycholecalciferol, which is the active form of vitamin D. I need the liver and the skin in the processing of this. The shortened name for this is calcitriol. And it's important in calcium and phosphate homeostasis, and it's a steroid hormone. Some other ones, and many of these may not talk about, the heart produces a hormone called atrial natriuretic polypeptide, which is fortunately a polypeptide. Macrophages can produce cytokines that can circulate, albeit briefly, in the blood. Those are polypeptides. The pineal gland produces melatonin, which is a polypeptide. Things which probably have already been covered with metabolism, etc., and digestion would be insulin, glucagon, and somatostatin from the pancreas, all polypeptides. Adipocytes produce leptin, which is a polypeptide. GI tract produces things like cholecystokinin, gastrin, and secretin, the big three of the digestive hormones, but also things like vasoactive intestinal polypeptide, gastric inhibitory peptides, somatomedin, ghrelin, and substance P, all polypeptides.
All right, so we could spend 2 hours going through each one of those hormones and trying to figure out what they do. You could also get on Wikipedia and it'll do the same thing. But the point is, so if we just
in the blood, those are polypeptides.
For instance,
the pineal.
Here, you know, vitamin D, critical for maintaining calcium homeostasis. Calcium is a major signaling molecule in a lot of cells. That second messenger system that a lot of hormones function through. Intracellular free calcium is a major signaling factor. Erythropoietin, making red blood cells. The renin-angiotensin system in the kidney is critical for maintaining blood volume. All right. So all these, you know, all these factors, all these hormones that we're talking about are part of the physiology of staying alive. And when we're sick, we're basically, it usually involves some of these hormones that have been mentioned. ANP is made by the heart, and it's a natural diuretic. So that's why it's called natriuretic polypeptide, and it's involved again in affecting the kidney to regulate the amount of water that's in the system. So the heart is saying, all right, there's not enough blood volume for me to squeeze out, so I'm going to make this hormone that will affect the kidney, you know, to let more water in or keep more, let more water out or keep more water in. So blood volume is incredibly important for maintaining the correct blood pressure. Okay? So this is the immune system, the damn macrophages. It's not just macrophages, it's all white blood cells, all right? And these guys, if you were to go through the list of cytokines, there's hundreds of them that are making factors that will regulate all the different subtypes of immune cells so that your immune system is working correctly. We really don't know what melatonin does, in a sense. It's made by the pineal gland. It's involved with circadian rhythms. That's probably its main role. So every night melatonin goes down or up, I can't remember which one. But in any event, you can take it to prevent jet lag or help you sleep. So it's available at the health food stores, but the amount that you need to take is probably a lot more than what's in those tablets in the health food stores. So, so all these hormones are important. What was the previous slide here? That was the ovaries. Sorry. Kidneys. And then there was another slide. Was this it? Right. So then you've got hormones that are made by the pancreas. Now, this is energy homeostasis. So insulin and glucagon. Insulin, we talked about, or you guys heard about that in the previous lectures, critical for maintaining, metabolic control. So the energy homeostasis, after you have a meal, glucose levels go up, that glucose gets transported into cells by insulin. Glucagon, it does the opposite. It acts on the liver to synthesize glucose from glycogen. Somatostatin is part of the regulatory system that controls the release of growth hormone from the brain. Okay? So growth hormone is part of growing. So it's called growth hormone. But it also affects metabolism and insulin sensitivity. And remember I mentioned placental lactogen? Placental lactogen has a lot of homology with growth hormone. That's probably how it affects insulin sensitivity. Leptin is an interesting one. We wouldn't be talking about leptin if this was the early 1990s, because nobody knew it existed. But leptin is a hormone that's made by fat cells. It's important because it is part of the satiation, I've had enough to eat system. All right? So leptin is made by fat cells. It acts on the brain to tell you that you should stop eating. It also acts on the brain to tell the reproductive system to function. So there's conditions, for instance, athletic amenorrhea, anorexia nervosa, where the number of adipocytes, the number of fat cells, or the production of leptin from the fat cells is so low that what that's doing is telling the brain there's no point in getting pregnant because the female doesn't have enough resources to keep this pregnancy going, so the whole reproductive system shuts down. Okay, so leptin is a way of the brain detecting how much adipocyte and fat storage is in the system, and if it goes below a certain level, then the reproductive system shuts down. And then we've got all these gastrointestinal tract hormones that I really don't know a lot about these guys, except that ghrelin is part of the satiation centers. There's some somatomedin in here. I don't know what that's all about because that's supposed to be a growth peptide. But the gut is an endocrine organ, okay? And this is something that has only come to light probably in the last 20 years, especially with things like ghrelin and gastric inhibitive peptide and all these other peptides that we're now beginning to understand these mini endocrine loops that are happening within the gastrointestinal tract. Okay. And they effectively all feed back on higher centers in the brain. So that the major control center in our physiology is the brain. A lot of the hormonal regulatory mechanisms that we're aware of are acting through the hypothalamus pituitary axis, okay? Either the posterior pituitary or the anterior pituitary. But there are also other higher centers in the brain that are also part of this regulatory loop. So So without all this, we can't maintain homeostasis. That's the definition of being alive, is that we can respond to our environment and we can keep our internal environment going in a way that sustains life. Okay? Any questions? No. Right, let's see. This one. So that's the endocrine system. Let's get that.
Is there a way that we could get access to these videos?
That's a good question. I guess that there should be. Yeah. I think I've got access because I'm me.
I think in Canvas there's a way to, like, if the instructor has access, you might be able to click some button to give the
I'll
students
tell
access.
the coordinator if you guys want access.
Thank you.
I'll let them know. Now, so we're supposed to be talking about the limbic system, and did we just do the quick summary? There's 2 quick summaries, part 2.
This is part 2 of the quick guide for endocrinology. This is intended for you to be able to use, let's say, when you were preparing for national boards, or if you just wanted to quickly go over and review the things we probably discussed in more detail in lecture. I'm not going to go through and talk about all the entries here. I'll just give you a quick introduction of how you could use this. So for instance, what we have here is information. First, starting with the hypothalamus. Quick summary. Releasing hormones and inhibiting hormones are synthesized and released by hypothalamic cells. That gives you an idea of what's going on with the hypothalamus. They enter into the hypophyseal portal system in the median eminence, and they travel to their secondary capillary bed in the anterior pituitary. So that gives you an idea about what's listed below and what it's probably involved in. Then we have a list of 8 hormones here, which we start this list with corticotrophin releasing hormone, abbreviated CRH, or CRF, where F stands for factor instead of hormone. Mean the same thing. And then a quick summary, a brief one, about some things about that hormone. It stimulates the release of ACTH by corticotrophs. So again, here's the cell that makes it, cells that release ACTH. They are located in the anterior pituitary. Now, CRF is released in response to stress, such as trauma or infection, cold or heat stress, or surgery. So it gives me some idea of what the stresses are. And it also peaks diurnally at around 8 a.m. as part of that diurnal rhythm. So it gives me a pretty quick summary. Well, here's what this does. Let's look at another one. Prolactin inhibiting hormone, also called PIH. And it turned out that they discovered prolactin inhibiting hormone was simply dopamine, or DA. It's released by the hypothalamus, and it inhibits release of prolactin. The name kind of tells us that. Prolactin is made by lactotrophs, or also called mammotrophs, and they're located in the anterior pituitary. So you can go through for each one of these and get a name, what other names it may go by, and a quick summary of what it may do. Okay, you get done with the hypothalamus, you move into the pituitary gland, divided into the anterior and posterior pituitary. So let's pick luteinizing hormone, or LH. It says triggers ovulation, and also thereby the formation of the corpus luteum. And that it also stimulates secretion of estrogen and progesterone in women, in case you were confused, and stimulates testosterone secretion by the testes in men, again, in case you were confused. Prolactin stimulates milk synthesis and secretion, but not release in women. So again, just quick hitting some key things, key points about each one of these hormones and what they may go by. After the pituitary, we have the thyroid gland, the parathyroids, the adrenal glands, and the concept of hypoadrenalism and Addison disease, hyperadrenalism and Cushing syndrome. The ovaries, what the estrogens are doing, progesterone, relaxin, and inhibin. The placenta, what's there and what's going on. Testes, the kidneys, the heart, macrophages, pineal glands, and then those things I said probably previously had covered and aren't covered here. So you take that handout and you can use it as a quick reference guide, and that may be handy also when you're preparing for national boards.
Very good. Let's see if we can find this lecture. It's a PowerPoint for the Limbic System.
It's different from the ones you went over in the video, but
Yeah. Do we want to go over this PowerPoint? Or do we just want to go home? Do you want to go over any other stuff in endocrinology that you might have questions about? I'm here. Here to move. I think we might do. We did that. So we can go through these notes, and where I can help you with any questions. The limbic system helps to explain how emotions and experience can impact hormone regulation. You know, that's a real can of worms. I was just at a meeting recently by the North American Menopause Society, talking about hormones affecting emotions and experiences. So, you know, menopause happens in women probably between the ages of 55 and 60, around that area, 50 to 60. And it basically happens because the ovaries run out of eggs and they can't make any more estrogen. So there's no more estrogens coming from the ovaries. And this affects all these systems in a woman's body. Hot flashes, my wife is still going through some hot flashes. She loves when the weather's cold. And we're constantly having arguments about the thermostat in the house and who gets to regulate that thermostat. So, you know, hormones affect the brain, especially steroid hormones, progesterone, estradiol. You just have to look around to see how testosterone affects the brain, for crying out loud. So there's a potent regulator of behavior. When I was a graduate student, we studied the role of the gonads and the pituitary gland in the development of prepubertal sheep, prepubertal lamb, and we took animals and randomly allocated them to a testosterone-treated group or a estrogen-treated group. And the ones that got testosterone, regardless of if they were male or female, we castrated them and whipped out their pituitary and then gave them testosterone. The ones that got testosterone were always first feed bucket, they were headbutting all the other ones. It increased aggression, they got more food. So, and we see that in dogs. Male dogs will cock their legs, but if you give a female dog testosterone, she will cock her leg when she pees. So when we talk about the limbic system, emotions, learning, all this stuff about hormones affecting the brain and behaviour, we don't have a good understanding of how it happens, but we know it happens, and it's all around us all the time. So they influence emotion. The limbic system, I'm just going to read through this, the limbic system includes a variety of critical conscious and subconscious, unconscious structures. So these are the critical structures, the prefrontal cortex, the temporal cortex. Now, an interesting thing about this is that in most animals, especially insects, you can see it in your dog, smell is a major stimulus for behaviour. Okay? And actually living in the world, the dogs use their snout more than they use their eyes. Okay? So we have lost our olfactory bulb has shrunk a lot. But the interesting point about this is that the cells that secrete the gonadotropin releasing hormone from the hypothalamus. Remember, the hypothalamus is making a hormone that's driving the pituitary, that's making FSH and LH, that's making us reproduce. Cells that make the GnRH from the hypothalamus are actually derived from the olfactory bulb. So smell and reproduction were linked, and this was discovered with a syndrome called Kelman syndrome in men. Men who were infertile, and they also had no sense of smell. And the reason that they're infertile is because during embryonic development, their olfactory bulb did not develop, and those cells that migrate from the olfactory bulb down to the hypothalamus to make those GnRH secreting cells, they didn't do it. So they had no smell and they were infertile. And so we learned from that experiment of nature that smell and reproduction are linked. So, we are not, the pheromones probably affect our reproductive strategy, but I don't know that we're that aware of it. We all wear, I don't, but some people wear cologne and all these different things. I remember when I was a graduate student, there was a reproductive biologist working in the department, Dr. Short, who's a famous reproductive biologist. He came around to everyone in the department and said, "Can you smell this? Can you smell this?" It was wild boar semen, and only 50% of people could actually smell it. The other 50% couldn't. And so he was doing a study on who can smell boar semen. And so I don't know what the outcome of that was, but the point of it was that we have this part of our brain that senses smell, and sometimes we don't perceive the smell, but it might change our behaviour. So pheromones are probably something that affects human behaviour and emotion, and it's all acting through this limbic system in the brain. Okay? So it affects the thalamus, the hippocampus, all these listed structures here, but importantly, in terms of endocrinology, it affects the hypothalamus. It may also affect inputs that are going into the pineal gland, and that could affect your circadian rhythms. So there's a goodly amount of structures in the brain that could potentially be affected by sensory input that will affect emotion. So here now he's got structures that play especially key roles and are interconnected by fibre tracts. So, boy, I was never good at anatomy, especially neuroanatomy. But this is basically outlining how emotions coming into the prefrontal cortex can link with other areas of the cortex. So he's broken it down into information processing and emotions, which sometimes, emotions can override, rational information. And you would imagine that this is critical. You don't want to, if you're walking down a track and suddenly a mountain lion shows up, you don't want to spend time rationalizing about the threat. You want to just respond. So the emotion is this rapid response system that we can get away from that threat. So I'm not going to go through all of this, but you can see that a lot of things are feeding into the hypothalamus. The hypothalamus is feeding into the pituitary, and then the pituitary starts making the hormones either from the anterior pituitary or the posterior pituitary that affect physiology. Okay? There's not a lot of feedback going on here, although there is feedback going from the reticular system to the thalamus. But, I guess as dentists, you've got somebody on the chair and they're a little apprehensive, as we all are, when we open our mouth and let somebody do stuff in there. Keep in mind that all these parts of the brain are being affected. And they could impact on your actual physiology because, as he's kind of rightly stated here, the pituitary is the master gland, and just by the last two videos, we heard that the hormones produced by this pituitary gland are critical for staying alive and maintaining homeostasis and normal physiology. These connections show how emotions, memory, consciousness, and endocrine function are intertwined. That's correct. So, for instance, emotions altering endocrine function and hypothalamus fear of pregnancy delaying menses. Oh, that's interesting. Fear of pregnancy delaying menses. I don't know that I buy that. Does anybody buy that? Fear of pregnancy delaying menses. That's basically saying that, if you have fear of pregnancy and you delay menses, you're actually promoting pregnancy because you're delaying having your period, which allows that blastocyst time to implant in the uterus. Fear of impotence, producing impotence. I'm not sure about that either. Well, it could happen. Depression altering feeding behaviour. Yeah, things like anorexia nervosa, which is really a neural disease. Antidepressants in inducing weight gain. So hypothalamus and endocrine altering emotions, premenstrual syndrome, menopause. I've just spoken about menopause. All these are basically, premenstrual. The hormones that change premenstrual are mainly progesterone, and that's because it's going down. That withdrawal of progesterone causes menstrual deprivation. Menopause is the lack of progesterone and estrogen in the system because the ovaries have shut down. There's also postpartum depression, which the key thing that happens postpartum is that the hormones are made by the placenta, of which the progesterone is the main one. Okay? As soon as that placenta is born, suddenly the mom that is marinating in progesterone for 40 weeks is not. So her brain is not seeing the progesterone anymore. So premenstrual stress and postpartum depression might have links there. Midlife crisis, I agree with this, this question mark here. What's this hypothyroid depression? I don't know anything about that, but I'll take his word for it. Some of us go through a midlife crisis every couple of years. It's kind of fun. Buy yourself a new car. So I don't know about this midlife crisis. It's something, because we use the term midlife crisis, it makes a midlife crisis happen. You know what I'm saying? Because now we have this word out there, there's two words out there that are saying, oh, I'm feeling a bit down and I'm 45, 50, I must be having a midlife crisis. So that amplifies the effect. Emotion-altering consciousness. Worry, producing sleep loss. Yeah, I can see that. Depression, producing somnolescence. Is that the same as sleep loss? Somnolescence. Do we know what that is? Could be too much sleep, actually. Worry, decreasing ability to focus. Yeah, so we're living in a complex world. Our brain's trying to process all these things, all these emotions. Our kids are doing stuff that we didn't expect them to do. Stuff happens and we have to deal with it, and this causes changes to our physiology. A few interesting disorders associated with limbic dysfunction, frontal lobe dysfunction, lobotomy, and tertiary syphilis. Isn't that interesting? So, I don't know, lobotomy is a procedure that they would do to psychiatric patients. They would cut off parts of the front of the brain in order to calm them down and help their condition. It's not done anymore. This was, I don't know if you all have ever seen the movie One Flew Over the Cuckoo's Nest. The main character in that was given a lobotomy at the end. He was basically a vegetable. The Jack Nicholson character. And this is in the 50s, when that was a standard therapy. I have no idea about tertiary syphilis. I have to look that up. Temporal lobe dysfunction, Kluver-Buck syndrome, fixation on stimuli. Isn't that interesting? I'm going to look that one up. Depression, low levels of 5-hydro, 5-HT. I'm not sure what that is. Rapey. What's that? Oh, yeah, okay. All right. Schizophrenia, and there's a beautiful mind. That's a good movie. So, all these things. This is why I find psychiatry so fascinating yet confusing. I mean, we're all living in our brain, and all these things affect it. And, interestingly, when you think about psychiatry and all these depression emotions, they all have a chemical basis. It's not like, it's just that we don't understand some of these chemical bases. It's a neuro and anatomical, chemical, hormonal basis for the things we feel and the way we perceive the world. Okay? So now he goes into the role of hypothalamus. And this basically reiterates what we just saw in the previous two videos, essentially. But the hypothalamus is that one integrating part of the brain. We've got higher centers feeding into the hypothalamus. That hypothalamus is taking all that information and converting it into signals that are affecting the secretion of vasopressin and oxytocin. So that's made directly by the hypothalamus. But then the hypothalamus is also making the releasing factors, releasing hormones that are controlling the anterior pituitary. And then everything downstream from there is affecting the target organs in the body that cause a phenotypic change, okay? Reproduction, dealing with stress, thyroid hormone, metabolism. And that event, or that phenotypic response, has a feedback to the brain. So the brain is detecting the world it's in. It's detecting the exterior world, the external environment, and the internal environment, and processing all that information so that the release of these hormones is balanced out, and we can, walk around and come to class, or not come to class, and do what we do to live our lives. And so in each of us right now, this whole thing is happening. It's nearly lunchtime. We're starting to think, is anybody hungry yet? You are now, because I said, is anybody hungry yet? You ever had that experience? Somebody says, I just got hungry, and all of a sudden you get hungry. And so, our brain is processing all this information, it's integrating it, it's somehow trying to make sense of it, and then the expression of that trying to make sense of it is the activity of these specific parts of the brain, particular hypothalamus, that then regulates our physiology. Okay. So thyroid release, CRH, we just went through all of those. So a lot of them are to do with stress, responding to stress, staying alive, running away from the lion. Metabolic regulation, so thyroid hormone is important for metabolic homeostasis. Prolactin, which should be an L, is involved with lactation. Okay, so we wouldn't be here if, as infants, we didn't have a source of nutrient. And so lactation is critical for us being on the planet. And then there are hormones that are involved with just responding to circadian rhythms of the planet. From the point of life on Earth, cells or life forms that developed in the sludge millions of years ago were exposed to light and dark, okay, because of the sun, the Earth revolving around the sun. And so circadian rhythms are part of our biology. People who work on circadian rhythms actually tell us that we should be treating ourselves in the lab at the same time every day, because even though they're stuck on the bottom of a dish, they still have their inherent circadian rhythms, their intrinsic rhythms. And then there's factors that will either stimulate the hypothalamus or inhibit the hypothalamus, and these are feedback systems. So, everything in us works based on feedback loops. And they're usually negative feedback loops. There's not very many positive feedback loops that happen, but positive feedback loops do exist. One of them is in the brain at the time of ovulation, where estrogen usually inhibits and then it flips to stimulating the release of gonadotropins, and that causes ovulation. Usually, if you ever come across anything in a physiology textbook where it says there's a positive feedback loop, that positive feedback loop will amplify itself. So that's not a good thing. But usually, positive feedback loops end up in an event, either birth or ovulation are the two things that I can give you examples of right now. And that event disrupts the loop. Okay? And when you get into one of those loops, then you get into an uncontrolled clinical situation in many ways. And a lot of pathology is because of positive feedback loops or feedback loops sort of drifting into this positive amplification state. Okay? Immune diseases, diabetes, you've got too much one thing around. Okay? So keep in mind when you're practicing that physiology is involved in feedback, is regulated by feedback loops. He went through these guys, these endorphins and enkephalins, all affect the brain function as either direct stimulators of parts of the brain or as neurotransmitters that brain centers use.